sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinalarla atan tüm mühendis adaylarını İTÜ Makina Fakültesine bekliyoruz. Makineler her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinelere hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makine mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya, elektronik malzeme ve demir çelik gibi makine imalatı yapan birçok sektörde çalışma imkanına sahip olarak mezun olurlar. Makineler dört tarafımızda. Hayal gücünün sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinelerle atan tüm mühendis adaylarını İTÜ Makina Fakültesine bekliyoruz. Makineler her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinelere hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makine mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya, elektronik malzeme ve demir çelik gibi makine imalatı yapan birçok sektörde çalışma imkanına sahip olarak mezun olurlar. Makineler dört tarafımızda. Hayal gücünün sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinelerle atan tüm mühendis adaylarını İTÜ Makina Fakültesine bekliyoruz. Makineler her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinelere hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makine mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya, elektronik malzeme ve demir çelik gibi makine imalatı yapan birçok sektörde çalışma imkanına sahip olarak mezun olurlar. Makineler dört tarafımızda. Hayal gücünün sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinelerle atan tüm mühendis adaylarını İTÜ Makina Fakültesine bekliyoruz. Makineler her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinalara hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makina mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya, elektronik malzeme ve demir çelik gibi makine imalatı yapan birçok sektörde çalışma imkanına sahip olarak mezun olurlar. Makinalar dört tarafımızda. Hayal gücünün sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinalarla atan tüm mühendis adaylarını İTÜ Makina Fakültesi'ne bekliyoruz. Makinalar her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinalara hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makina mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya, elektronik malzeme ve demir çelik gibi makine imalatı yapan birçok sektörde çalışma imkanına sahip olarak mezun olurlar. Makinalar dört tarafımızda. Hayal gücünün sınırlarını zorlayan, bu hayal gücünü yaşamın her alanında insanlığa sunmaya hazır ve kalbi makinalarla atan tüm mühendis adaylarını İTÜ Makina Fakültesi'ne bekliyoruz. Makinalar her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinalara hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makina mühendisi
full professor of engineering, and he had his Bachelor of Science degree in engineering in 1995. He had the Master of Science degree in 1999 and a PhD degree in 2005. His degrees are the Bachelor of Science degree is in marine engineering and the others are in energetic department in this University of Science and Technology in Oran University. He is an expert in thermodynamics, refrigeration, exergy analysis and CFD. He has an impact factor of 9 in Mendeleev ranking system and he has authored 21 journal papers, and he is here as a guest speaker for through the Erasmus program, and the title of the speak is on refrigeration, and we have 4 courses on that. Today we have the first and the second courses. These are on fundamentals of refrigeration, thermodynamic properties of refrigerants and vapor compression refrigeration systems. Tomorrow, starting at 11 a.m., we will have the innovative refrigeration systems, which are low temperature refrigeration systems such as air separation processes, natural gas liquefaction, liquefaction process, and non-conventional refrigeration systems such as vortex tubes and absorption refrigeration systems. I thank him for coming, and I will leave the ground to him for his wonderful speech. Thank you.
Thank you, Ersin, and thank you for your attendance. So, as Ersin introduced me, I am Ahmed OUADHA. I am from the University of Science and Technology in Oran, in Algeria. Algeria is situated in the north of Africa, and Oran is in the south of Algeria. Algeria is a big country, is the biggest in Africa, and Oran is near the Mediterranean Sea in the south. Yes.
Is it there?
Yes. In the Oran is here in the west of Algeria. Oran is the second biggest city in Algeria. There are some photos of the city, and here are we talked about with Ikram about the mosque. This is two mosques from Oran, and this one has been built by a Turkish company, Tosyali. You know Tosyali, iron company, iron steel company, Tosyali. Yes. And Oran is also an industrial pole where there is the liquefaction plants of natural gas. And you know that Turkey is a supplier, is a consumer of natural gas from Algeria. They have a gazoduct from. So you have a pipeline from Russia, I think, and the LNG, or the natural gas, liquefied natural gas, is from Algeria. And Tosyali is also in Oran. Tosyali, the company, the Turkish company. In Oran, there are three universities, among them USTO, University of Science and Technology, and one polytechnical school, and an institute of telecommunication. This is the university, our university, University of Science and Technology. It's a big one. There are 5 faculties, one institute of sports, and a language learning center. There are about 20,000 students in our university. I am also the head of a research group on marine propulsion, and my work focused on thermodynamics, the application of thermodynamics in refrigeration and cryogenics. Here, for example, there is a cascade refrigeration cycle. It is a liquefaction plant, the first one built in the world. It was in Oran in 1964 by a French company, Technip. Technip is a French company that built this plant. I worked also on LNG boil-off reliquefaction. This is a system used on board ships. We also studied cooling, non-conventional cooling system, about absorption refrigeration system. and waste heat recovery system. So on board ship, there are many waste heat that we can recover it to produce energy or to produce cooling effect using absorption refrigeration. We worked also on vortex tube. We'll see tomorrow about vortex tube. It's a mean of producing cooling and heating. And on heat transfer, organic Rankine cycles, heat transfer also, and hydrocarbon refrigeration, refrigerants and combustion. Here also I have been in Spain for 6 months for postdoctoral training, and I worked on a supply system for a dual fuel diesel engine. Now we go directly to our lectures. So I divided the lecture on 4 parts. We are going to see the first one. The first one on fundamentals of refrigeration. What does mean refrigeration? And the second one about thermodynamic properties of refrigerants. Refrigerants are the fluid used in refrigeration systems. The second one is the cycles and schematic diagrams of one stage refrigeration system or single stage refrigeration system. Then we go to the low temperature refrigeration system, and we finish with non-conventional refrigeration systems. So I begin by the first chapter. So as you know that on thermodynamics there are two principles or 2 laws are very important, the first and the second one. The first one, sometimes I ask questions. The first one is the first law of thermodynamics. You can participate, it's a lecture. The first one is energy, too simply, energy conversion, conservation. That means that energy that enters the system is the same that exits the system, simply. And for the second law of thermodynamics, there are many definitions. Among them, the definition of Clausius, who said that, you know that heat will transfer from hot to cold. If we have two bodies, A and B, with temperature A and temperature B, so the heat will, in this sense, if T is greater than TA, greater than TB, you know it. So Clausius said that it is impossible to do the other sense, to transfer heat from the cool body to another hotter. If we do that sense, the non-natural sense, from low temperature to a high temperature, we need to supply energy. This is the principle of work operating of refrigeration system. For a refrigeration system, we need to give energy. In a refrigerator, we need to plug. Why? The plug is for the electric motor that drives the compressor. So we need to give energy, and the refrigerant will remove heat from the medium, the cooling medium, and take heat to the environment. So a refrigeration system is here that work as claimed by the second law of thermodynamics between 2 sources, a hot source and a cold source. And refrigerant will need energy, W here, we need energy, and with that energy, it removes heat from the medium, the cooling medium, and reject heat to the surrounding. It is the inverse or the opposite of an engine. In engine, I can, how to, yes. In an engine, it's also work between two sources, a hot source and a cold source. But in engine, we give heat. We give heat, the energy in the fuel. We give heat after the combustion. There is an energy, there is a heat. We give heat here. And the heat, a part of the heat is converted to work, useful work, and the other is rejected to the environment, the surrounding. But here in refrigerant is the opposite trend. We give energy, then the machine or the system will remove heat from the medium of cooling. So the first who think about thermal system is Carnot. You know the Carnot cycle? That, and he developed a theoretical cycle called Carnot cycle. A Carnot cycle is composed of two. It's composed of two or four processes, theoretical processes, two adiabatic reversible processes, and two isotherm processes. This no. This is adiabatic reversible, 1, 2 adiabatic reversible, and 3, 4 adiabatic reversible. Adiabatic reversible, it means that the entropy don't change. There is no losses. Entropy is still constant. And two isotherms here, 2, 3, and 1, 4. This is the reversed Carnot cycle. The direct Carnot cycle is for engines. So in refrigeration, in engines, we define the efficiency. Efficiency is equal to the work or the power produced divided by the energy supplied. But in refrigeration, we define another parameter, another criteria. It's the coefficient of performance. It's the ratio of the heat removed to the energy supplied. And you know that for a refrigeration system, maybe work as a refrigerator to produce cooling or produce heating as a heat pump. So we define the two coefficient of performance for refrigeration. It's Q, this Q, removed from the cooling space, divided by the energy supplied. And for a heat pump, it's the heat given to the heating space divided by the energy supplied to drive the compressor. And if we replace this one, I can do a demonstration of that, what has been Q.
Otherwise it doesn't go back.
Okay.
It has to touch.
I'll explain rapidly this. Donc we have in a temperature entropy diagram the Carnot cycle, the reversed Carnot cycle. 1, 2, 3, 4. And I'll define another point A and B. So the heat removed from the cooling space is QL, and the heat rejected to the heating medium or the environment is QH. So QL here is that area. It's a rectangular. The area is a rectangular. It means that distance multiplied by that distance. Here is, I define two temperatures, TH and T low and high temperature. So this QL is the area for 1B/A4. It's a rectangular, so the surface is, the area is that TL equal TL factor SB moins SA, this one. SB minus SSA. The same thing for QH is the area. QH is all this area. All this area. So it's 3, 2, 3, A, B, 2 equal TH SB minus SA. And we can define W, the work done on the cycle. It's the difference between the two, or simply the surface inside the cycle. So it's TH minus TL SB minus SE. And if we do the definition of the coefficient of performance, we get the result are for the coefficient of performance for refrigeration mode, it's equal to TL divided by the difference between temperature. And for the heating mode is TH divided by the difference of temperature. It means that for a Carnot cycle, a machine that works on a Carnot cycle, the coefficient of performance or the performance of the system depends only on the levels of temperature. They don't take into account the refrigerant, only on the level of temperature. And you have a relation between both. COP-IH, heat pump, equal COP refrigeration plus 1. But we'll return on the Carnot cycle in the second chapter to say that it is impossible to have a machine that operates on the Carnot cycle. Now we go to the thermodynamic properties of refrigerants. Refrigerants is the carrying or the heat carrying medium that carry heat from the cooling space to the environment. The fluid used in a refrigeration system is called refrigerant, to simply refrigerant. And to use the refrigerant, or to study a refrigerant system, we need to calculate thermodynamic properties in point of the cycle 1, 2, 3, 4. To calculate thermodynamic properties, we have three methods: using thermodynamic diagrams, or using thermodynamic tables, or using a set of equation of state. Before detailing this method, we have in engineering, when we use, in any study, when we use a fluid, we have two possibilities. We consider the fluid as an ideal gas or as a real gas. We can use, for example, in engines, we use the assumption for an ideal gas. But an ideal gas doesn't exist. Can you tell me why? Why we use ideal gas? You remember all in thermodynamics, you have used PV equal to RT. You remember it? No. It is an equation of state of an ideal gas. And we use ideal gas, for example, if we want to calculate thermodynamic properties of air in this room, we use PV equal to RT. It means that we suppose that the air is an ideal gas. So, to suppose an ideal gas, we have three points. First one, molecules of the gas, if the molecule of the gas have negligible weight, they haven't weight, like R here. When you do like this in R, the molecules haven't weight. For example, you do in water, they have weight. In vapor, yeah, they have weight. The second point is absence of interaction forces between molecules. There is no interaction between molecules. In a liquid, there is interaction between liquids. In a solid, there is more force interaction between molecules. And the third one, an ideal gas obeys to the equation of Clapeyron, or equation of ideal gas, PV equal to RT. In this room, if we consider the pressure one bar, and the temperature now it's about 24, 22 degrees, and we calculate P, we know the volume, we can have PV divided by RT very close to 1. So we can use with a good approximation the assumption of ideal gas. But in some cases, where this one of the 3 points is not do not work, like in refrigeration system. Why? In refrigeration system, the refrigerant passes through compressor. It is in the gas phase. Then it passes in a condenser. It's change phase. So there is the apparition of liquid state. So where refrigerant is liquid, it is not an ideal gas. We can't consider it as an ideal gas. It is a real gas. It's clear? If you have a question, you can ask question at any time. So the first, for real gases, for example, for application, you have for engines, for diesel engine, auto engine, auto cycle, you use ideal gas assumption. For Rankine cycle, when you for steam turbine, organic Rankine cycle, refrigeration system, we can't use the assumption of ideal gas. We have to use the real gas assumption. To calculate a system where the fluid is a real gas, we have the 3 possibilities: diagrams, tables, or equation of state. For the diagram, there are six diagrams. Among them, diagram pressure enthalpy is the most used in refrigeration system. It is diagram enthalpy H, pressure enthalpy. It's like this. She has a shaped curve that limits phases. Here is vapor or gas phase. Here liquid plus vapor, and here liquid. And this point is the critical point. It depends on refrigerant. Each fluid has its own critical point. And the same thing is each body, each matter has a diagram with critical point, triple point, etc. So here we can, for the advantage of diagrams, that we can see the evolution of elementary processes. For example, you have in a heat exchanger, pressure remains constant. You know, here, for example, if we want to use heat exchanger, a condenser to pass from vapor to liquid, it's pressure constant pressure. We use an evaporator here, it is a constant pressure. We use, for example, a valve for, or a tube in a refrigerator. You have in the domestic refrigerator there is a tube like this. A tube is capillary tube. In a tube or a valve, enthalpy remains constant. So this is the advantage of using diagrams. We can show the evolution, isobaric ovulation, pressure is constant, isothalpic evolution, enthalpy constant, and we can see like this is entropy constant. We can define the quality X, the quantity of vapor in a point. The quality here, this is the liquid, saturated liquid. And this is, from here, the saturated vapor. So here is 100% is one vapor, and here it's 0 vapor. The X quality, X is the quality, it means the mass of vapor contained in a point. The second mean of calculating thermodynamic properties of real gases is the utilization of tables. Tables are prepared and for two parts of tables. One part is the saturated, it means it gives only properties on this curve. This is the saturated properties or properties of saturated. Here, for the example, is propane. And the second one is the properties of the gas phase here from this part here. And using the two tables, we can define any properties. Here, when using the first one, we need to know just one property to determine the other properties. For example, if I in the first table I have temperature, I can define the other parameters like density, enthalpy, and entropy. But in the second table, when I am here in the gas phase, I need two parameters to determine the other parameters. For example, I need to determine pressure and temperature. For example, I need to have pressure and another parameter, for example, entropy. And the third one is the utilization of equation of state. You know that the origin of equation of state was van der Waals, who developed an equation of state what did van der Waals? We have the equation for an ideal gas, PV equal to RT. The first point was, the first point to consider an ideal gas was interaction. Interaction is the second one. The weight. So he corrected the weight by another parameter. The weight, it means the volume of the molecule, corrected by another parameter, parameter B. And he corrected the pressure because the no interaction has a relation, direct relation with pressure. If the pressure is big, then there is interaction between molecules. So he corrected the pressure with another parameter, A divided by V2. And he developed its equation of state, the first one developed. And after, there are many other equations, among them SRK, equation of state, Peng-Robinson equation of state, and the virial equation of state. The first one, van der Waals, SRK, Peng-Robinson, and the others are empirical equation of states. But the last one, virial equation of states, has a theoretical basis. It means for we can PV divided by RT, we can write it like this: B multiplied by rho C. This is the virial development of an equation of state. So when rho tend to 0, we have PV divided by RT equal 1, it's ideal gas. So it means that for low densities, the real gas is considered as an ideal gas. So here, the second virial coefficient, the third virial coefficient, and the fourth virial coefficient have a theoretical basis. The definition, it means that the second one is the interaction force between two molecules. The third one, interaction force between three molecules. And the fourth, between four, and so on. Any question?
Do you use the NIST database for these coefficients? NIST, National Institute of Standards and
NIST database have many equations of state, among them Peng-Robinson, SRK. They haven't the virial equation of state. They have another approach to calculate thermodynamic properties. For people who are using in Fluent, there are NIST database. You can choose among equation of state. For people who are using, for example, software for systems, do you use HYSYS? HYSYS, no?
I use RefProbe sometimes.
RefProbe is NIST. RefProbe is NIST. RefProbe is from NIST. They use their own equation of state. Now, HYSYS is a thermodynamic for thermodynamic analysis of a system. You have also some equation of state. The problem that equation of state, for example, Peng-Robinson, has been developed for only hydrocarbons. When you use it for example, water, it doesn't give good results. Other question?
This formula, has it got any special approximation method?
What formula? This one?
Yes.
No, we can.
Just formula, or any approximation method?
This is the development of virial development. So B, we can get it from, for example, we do experiments, and we get B. B is function of temperature. It is not a constant. B is function of temperature, C is function of temperature, and D a function of temperature. And we can determine it using statistical thermodynamics. So using the force interaction force between 2 molecules, 3 molecules, and 4 molecules, and etc. Others question? You can ask any question, any question. So, if there is no question, I continue. Generally, there are two types of thermodynamic equation of state. There are unified equation of state. That means that an equation that gives all properties in this thermodynamic surface. For vapor, liquid plus vapor, and liquid. It is very complicated, and it contains a lot of number of parameters, and it is rarely used in engineering. The second method is to use local equation of states. And generally, we use the fourth equation of state. The first one is an equation of state for just the gas phase. The second one is the pressure, saturation pressure, vapor saturation pressure as function of temperature. The third one is the saturated liquid density as function of temperature. And the last one, the fourth one, is the specific heat capacity at constant pressure at the ideal gas state. Because we know that we have ideal gas is the limit of real gas when densities tend to 0. So for equation of state, there are two possibilities. Using unified equation of states, it means an equation that cover all the thermodynamic surface, gas and the liquid phases, or using a set of equation of state composed generally of fourth, an equation of state for the gas phase. It is, for example, pressure as function of temperature and density. The other one, the saturated vapor pressure as function of temperature. The third one, the saturated liquid density as function of temperature, and the fourth one is the specific heat capacity as function of temperature at the ideal gas state. From this fourth equation, we can derive expression for enthalpy, entropy that we use to calculate the system using thermodynamic differential equation of thermodynamics. You know that for fluid, you know that there are differential equation. There are also for thermodynamics. There are this equation. For example, for enthalpy, we use this. It means I have an equation of state P as function of T and V, or density rho. I derive, multiply by T, then I derive V, multiply by V, and I do integral for that to get an expression for enthalpy. I do the same thing for entropy, the same thing for heat capacity at constant volume, and the heat capacity at constant pressure. Question?
For example, first one, the temperature is a constant. Maybe they don't know the meaning of the subindex.
I give an example. I give an example here. For example, I have an equation of state of the gas phase case, P equal RT van der Waals minus I. I have another equation to determine enthalpy and entropy. I need only the gas phase equation, P as function, this one, you see. The first one, P as function of T and V. And I need the last one, Cp, 0 for ideal gas, for example. To determine from these two equations, to determine the enthalpy, I need the enthalpy to calculate the cycle, I need the enthalpy, I need the entropy. To determine it, I use the differential equation of thermodynamics. For example, the first one, dH dV at constant temperature equal the first one, T dP per dt. We derive dP per dt. It's equal. When you derive this one, this is R T. It's only R divided by Vm1b. 0, this is 0, it's a constant. And we derive the second one, V, we derive P or V.
Now T is a constant, since it is suffix.
T is constant, we derive RT divided by Vm1b minus B, derive is RT divided minus Cc minus RT divided by 1b square minus A divided by V square, derive to A divided by V. To A divided by. Then to determine the H, we need to do, if I calculate delta H, we need to do integral of this RT divided by Vm1b minus integral RT divided by Vm1b plus 2a IV integral dV dV. This is the contribution of real gas. Then I can do this for real gas, air, and the real enthalpy of the gas, delta H, is delta H air plus integral of Cp0 dt for the contribution of the ideal gas. This is the expression of enthalpy. I give in the
Departure, I think. The first
departure, yes, departure.
Yeah. We have them on the diagrams at the back of Chengar.
Yes, departure number. Have you given them the lecture in PDF? No. In the PDF, you can give them the PDF. In the PDF.
Didn't know who is coming. Maybe we take an attendance.
course. In the end of each chapter, I give exercise. Among the exercise, this one to. So we get the expression for enthalpy. You know that for enthalpy and for entropy, we calculate just delta H, delta S. So we need a reference state here to determine the integral constant of integrals. We need a reference state. It does mean that for enthalpy, if you are using a reference, for example, an American reference, you should have another reference state. You use a reference from Russia, you get another reference state. But the delta H is the same. So the reference state is arbitrary. You can choose any reference state. The delta H will be the same. You understand? It means that values of enthalpy, you can, from a book, from another book, they may change. They may be different, but the difference will be the same. I think.
They thought it a kind of an attendance, and they tried to vanish, you know. Different books can have different references. The actual value in the thermodynamic table can change from book to book. That's why if you are continuing somebody else's calculation, you have to check a known value, if it is consistent or not, because the other scientists may have been used another source, so you should be using the same source. So you have to double check it before continuing the previous calculation.
If you are living in the same world, why they are different? So they are just physical constants, right? So we are very different.
We live in the same world. Yes, but I said that the reference is arbitrary. You can develop your own equation of state, and you choose your reference. For me, I calculate the delta H. It's the same thing. I use your reference, the reference of others. I find the same thing because we calculate delta H. It's not absolute. For enthalpy and entropy, there are no absolute values. There is also a delta H difference.
Only for pure crystals, you have absolute entropy. It's zero Kelvin. So, for example, for a refrigerant like propane, you cannot define an absolute entropy. That's the reason tables may differ from each other. Maybe you can show them how to populate a table.
I try to for this is a free software called Pack. Why it is not? Okay.
Okay.
This is a free software developed by a university from Denmark, and there are many interesting things about how to calculate cycles and about thermodynamic properties. So for thermodynamic properties here, it's a Coolpack. Coolpack, you can download it. It's free. Coolpack. For thermodynamic properties here, we have diagrams and tables. Diagram, for example, for enthalpy, pressure enthalpy, temperature entropy, and here is enthalpy entropy, the most used in Rankine cycles. And this one is used for both. And this one, log P, pH, is most used for refrigeration. For example, I use this one. I have to choose among refrigerants. I use any refrigerants. For example, this one, I get the diagram. You can print it and you can use it for your work. This is for diagrams. I can use tables here for saturated tables. For saturated tables, I can choose temperature in centigrade degrees or in Kelvin. I can use pressure. I can use the maximum temperature and the minimum temperature. And the reference here is the reference state. Reference, I have the default. The default, they use the reference from the International Institute of Refrigeration of Paris. It is a French institution for refrigeration. The default is H at the saturated liquid at 0 degrees equal to 200 kilojoule. And S entropy at the saturated liquid at 0 degrees equal to 1 kilojoule per kilogram Kelvin. For example, I take the default here, the default, and I'll verify if at the 0 degrees, of the saturated liquid enthalpy is 200 and enthalpy is 1. So, OK. I go to 0. Here, 200 and 1 for the saturated liquid, SL and HL. It is arbitrary. I do the same thing for the same refrigerant. I do reference. I choose another one. For example, for the American Society of Heating and Refrigeration and Air Conditioning, ASHRAE, they use HL and SSL equal to 0 at minus 40 degrees. I choose this one. OK. I go to minus 40. It's a refrigerant where there is no minus 40, or I choose another one.
It's an intermediate one for LNG, correct? R14. R14 is an intermediate refrigerant for LNG production.
R14.
I use it.
What is the difference between this thermodynamics table and this data tables?
He is showing how to use them. It is much more practical.
Yes. And we can use another reference, this one, by default, or you can specify your reference, because it is arbitrary. But the difference between two values, delta H, it's the same for all references. What is your question?
I values of temperature. It's not available in the thermodynamic tables generally.
What?
In thermodynamic tables,
Thermodynamic tables, generally for the saturated, there are two types of thermodynamic. The saturated one is from the triple points to the critical points. It's limited. And the other one, the superheated vapor or gas, you can get unlimited as you like. And your question?
like my question was like in thermodynamics table in general that we use in from the Jangles book, like those have the temperature values are like from 0 to 1000 or whatever it is. But here I'm looking like there is a negative value of temperatures.
It's the fluid. It's a characteristic of the fluid. Each fluid has its own properties. Some fluids have the critical points, for example, the critical points very high. I take the case, for example, for ammonia. Ammonia has a very high temperature, it's exceed 100 degrees. And for other fluids, for example, carbon dioxide has temperature around 30 degrees. So the table will be shorter than, for carbon dioxide will be shorter than ammonia. It's a characteristic of fluids.
These are derived from some formula or just absolute values?
We can, the formula is, they are the equation of states. You can develop them. You can use in these tables, you can develop your own equation of state. And sometimes for CFD user, they need, for example, they need CP or they need thermal conductivity in a limited range. For example, the range is between 30 and 100, so they can develop just a polynomial variation, and it's a good approximation. Other question?
If we cannot select the reference is arbitrary, how could it promote the research?
It's the same thing. The result is
just same things.
the same things because we need delta H. I can explain it in temperature. In temperature, in degrees, T1, 30 degrees. In Kelvin, T2, 14 degrees. In Kelvin, 313 Kelvin. The difference T1 minus T2 or T2 minus T1 equal to 10. 40 minus 30 equal 10. 313 minus 303 equal 10. So when you calculate the difference, the delta, the reference is not important. It's arbitrary. It's really arbitrary. You can choose any reference state. The problem is that when you use books, the origin of books define the reference. You use an American US book, you have the Ashray book. It means that zero enthalpy of liquid and entropy of liquid are equal to 0 at minus 14 degrees. You use a French book, you use another book, you have 201 for enthalpy and entropy. Other question? For your question about tables, I give you examples. I go to saturated tables, for example. Saturated tables. I choose among refrigerant. I know that some refrigerant, for example, I take ammonia. Ammonia, the critical temperature is 132. and by default, it goes from minus 46. Minus 46 is the normal boiling point. You know, normal boiling point is the temperature that corresponds to 1 bar, to the atmospheric pressure. For ammonia is minus 46. It goes to 132 is the critical point. So I can get the table minus 46, and it is just until 132, the critical point, 0.35. It's so long. I take the same table, another table, for a fluid that the critical temperature is low, like, for example, carbon dioxide, or like for example, ethane critical temperature is 32, only 32, but the normal boiling point is minus 183. So I get the table is another table from 100 until 32. So generally, thermodynamic tables, saturated thermodynamic tables are given from the normal boiling point to the critical point. Other questions? So so I said that the reference test is arbitrary. Then we need to calculate enthalpy and entropy on this curve. This enthalpy, what I calculate, this is for the gas phase. Then I need to calculate on this curve, the saturated one. I use the equation of Clausius-Clapeyron, this equation and this equation. We use for this development, I use just two equations. I used Cp and P as function of T and rho, or V. And then I use the two others, Ps as function of phi here, I have to derive it, and I use the here the liquid, the density of liquid, or the specific volume of liquid. To get double prime, it means saturated vapor, and prime is saturated with liquid. So we use the equation of Clapeyron, dPs dt, T, H prime, second prime, H prime, equal the same thing as so from this we can define H prime and S prime. The same thing. You can for saturated liquid, you can S prime. You can find in a book SG, in American book. You can SF, not G, SF. You can in another book you can SL. For vapor, you can put double prime, you can SG, and you can SV. Vapor. Then we need sometimes in refrigeration cycle, we are here in a compressed liquid. In a compressed liquid here, so we need properties, and properties we calculate from these two equations for enthalpy and for entropy. So now we know how to calculate thermodynamic, how to determine H in each situation, in gas, in compressed liquid, saturated, or in here inside the curve. So we can pass to another chapter, another part of the lecture, to refrigeration cycle. So I can, when I design a refrigeration system, I can calculate the cycle. I can calculate performance of the cycle because I know how to calculate thermodynamic properties. So the second chapter is the refrigeration. Any question? You want to continue or to have a break? No? As you like, as you. For student. You want a break?
Yes. Can we?
Yes, you can. You can have break, and we continue.
For how long?
10 minutes maximum. And for you, just 2 minutes or 3 minutes. 10 minutes. I want question. I am sure that this.
Makineler her alanda hayatımızı kolaylaştıran insan uzantılarıdır. Makina Fakültesi'nde bu makinelere hayat verecek projeler geliştirerek geleceğe yön veren öğrenciler yetişir. İstanbul Teknik Üniversitesi Makina Fakültesi bünyesinde 2 bölüm bulunmaktadır. Bunlar makine mühendisliği ve imalat mühendisliğidir. Bir makina mühendisi soyut düşünür ve bu düşüncelerle geliştirdiği fikirlerin tasarımını hem günümüz hem de geleceğin teknolojisine entegre edip geniş ufuklara yelken açar. Mekanik problemlere analitik çözümler üretir. İmalat mühendisi ise uygulamaya konulmuş ya da konulacak bu soyut düşüncelere daha iyi tasarım, imalat ve montaj yöntemleri geliştirerek ürün ortaya çıkana kadar tüm evrelerde görev alır. En hızlı, en kaliteli ve en düşük maliyetle somut hale getirir. Öğrencilerimiz Makina Fakültesinden otomotiv, uçak, beyaz eşya,